Hello everyone. Let's wait for a few more minutes. Let others to join. Then we will start at around 7:10 or 12. Hello, am I audible to you? Hello, can you all hear me? Hello, can anyone hear me? Please reply. Okay, so we will start now. It's already 7:12. So welcome all of you again for the fifth interaction section, which is based on week 5 lectures of atomic and molecular physics for NPTEL course for January 2023 session. We will discuss a few problems regarding which will be covering the course content of the week 5 lecture of the NPTEL course. So let's start with our first problem of the day. So the question is, the ground state of chlorine is 2p3 by 2. Then find the Landes G factor for it and the number of substrates into which the ground state will split in a weak magnetic field. So in this question, what is given, we have been, so it is given that the ground state of chlorine is 2p3 by 2. So for chlorine, what is the atomic number for chlorine? Z equals to how much? Can anyone tell what is the atomic number for chlorine? For chlorine, we have Z equals to 17. So the ground state of chlorine is 2p3 by 2. But we have to find in this question, it is given that find the Landes G factor for it and the number of substrates into which the ground state will split in a weak magnetic field. So we know generally what we write for the ratio between magnetic moment and the angular momentum, like mu L vector by L vector mod is E by 2m. Here there is another term which is GL, which is called as gyromagnetic ratio, which indicates that what is the ratio of the magnetic orbital magnetic dipole moment produced for a unit of orbital magnetic moment of the electron. So here GL is equals to 1. So that's why we are getting this, but actual relation is mu L vector equals to minus GL L E by 2m. So for orbital angular momentum, GL is 1. Similarly, if we consider spin, then we have GS, which is gyromagnetic ratio for spin, and for electron, since electron has S half, so for electron we have GS is equals to 2, and from the above relation, like we discussed for orbital case, so for spin case, mu S by S, the ratio will be equals to E by M, where we have the ratio is actually E by 2m into GS. For this, if we put GS is equal to 2, so we get mu S by S is equal to E by 2m. So similarly, when, as you can see here, it is given 2p3 by 2. So for 2p3 by 2, What will be the s value? Can anyone tell for 2p 3 by 2 what will be the s value? So as we know that this term 2, if we compare the term with spectroscopy notation 2s plus 1 lj, then if we compare these two, this term and this given term, then we will get 2s plus 1 equals to 2, so which gives s equals to half. And for t l equals to 1, so l equals to 1, and here we know j equals to l plus s or l minus s. So for 2p 3 by 2, s equals to 1, l equals to 1, and we know that j equals to l minus s plus. So when we consider the total angular momentum, so it is a vector addition of spin angular momentum and orbital angular momentum. So we have l plus s mod 2 l minus s magnitude with increasing order of plus 1. So the next term will be l plus s minus 1 and l plus s minus 2, like that up to l minus s mod. So when s is equals to half and l equal to 1, so j will be 1 plus half to 1 minus half, so which is 3 by 2 and half. So if we consider the terms coming from this combination will be 2p 3 by 2 and 2p half. But here it is given, in the question it is given that the ground state of chlorine is 2p 3 by 2. So out of these two states, 2p 3 by 2 is the ground state. So how this ground state is determined, we will be discussing about it in future weeks, because these there are certain rules regarding the distribution of electrons in a level. So basically here what we have taken, if the orbital is half filled, then the ground, if the orbital is less than half filled, then the ground state will be the lowest j value, that is l minus s value. But if the orbital is more than half filled, the last orbital is more than half filled, then the ground state will be l plus j value. So this is basically Hund's rule, and which are used for arranging the electrons or determining the different state, arranging the energy levels in increasing or decreasing order of their energies. So basically, if we consider chlorine Z equal to 17, then according to Abba's principle, what will be the configuration of um, what is the configuration, electronic configuration of chlorine? We know from Abba's principle it is 1s, 2s to p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, like that. And we arrange electron in increasing order of their energy, like first we will enter electron into 1s, then 2s, then 2p, then 3s, like that. Then so we will arrange first in 1s, 2s, 2p, 3s, 3p, 4s, then we will arrange 3d, 4p, like that. So if we arrange, then the order will be like, so if we arrange 17 electrons, the order will be 1s2, 2s2, 2p6, 3s2, 3p. How much? For 17, what will we have? 3p 5. So this is the last orbital in which the electron is present. So we know that for 3p, for p l equals to 1, so ml value will be plus minus 1 and 0. So ml will be 1 0 minus 1. So we have, so if we arrange 5 electrons, then it will be arranged in this manner. So here, as we can see that the maximum capacity of p orbital is 6, but here we have 5. So this 5 electron is obviously greater than half filled, because in case of half filled we will be having only 3 spin up or identical spin electrons, but since it has 5 electrons in its p cell, so we will arrange 5 electrons in this manner. So out of which we are getting this. So this last electron is on the last electron pair. The last electron has not formed any pair. So here, due to this, there are different spectroscopic notations arising from the spin orbit interactions, and since the outer cell is more than half filled, so the ground state will be L plus S, that is 1 plus half, which is 3 by 2. So here in question it is given that the ground state of chlorine is 2p 3 by 2. So if everybody understood why ground state of chlorine is 2p 3 by 2, not 2p half, anyone have any doubt regarding this? Hello, am I audible? So basically, the main reason why here J is equal to 3 by 2 for ground state, because for 3p, the number of electrons present in the p orbital is 5, which is more than half filled, and according to Hund's rule, for more than half filled, the ground state corresponds to highest J value, that is J equal to L plus S when there are more than half filled. So for P, here P, L equal to 1 and S equal to half for electron. So 1 plus S, so 1 plus half, that is L plus S equals to 3 by 2. So chlorine has ground state of 2p 3 by 2. So in question what is given, find the Landes G factor for it. So first, so then we will first find the Landes G factor. So we know, like mu L, like here mu L by L, like here we considered mu L by L equals to E by 2m, that is GL into E by 2m, here GS into E by 2m. So like that, when there are both mu L and when there are L and S both, then they will interact with each other to produce total angular momentum, which is J, and the relation is also given by mu L. So similarly, the algebra is same, and we have mu J by J is direct proportional to Gj. So Gj is the Landes G factor, and the value of G, as discussed in week lectures, is G equals to 1 plus J square minus L square plus S square divided by 2 J square. So So this is the formula for Landes G factor, and if we consider quantum mechanical, then we have J is equals to J into J plus 1 square root into h cross, where h cross is the unit for h cross has the unit of angular momentum, and J and the J values are regarding the the energy levels. So here if we put what will be J square, then J square will be J into J plus 1 into h cross square. So here J square, L square, S square, for each Like L, for L also we have L equals to L into L plus 1 root h cross, and for S also the algebra is same, that is S into s plus 1 root h cross. Basically these are the solution of the differential equation which comes from the quantum mechanical Schrodinger equation um, of a atom. So when we analysis the atom on the basis of quantum mechanics and solve the Schrodinger's differential equation, then we get the values of these in these angular momentum. So for orbital angular momentum, the relation is L into L plus 1 h cross, and similarly all angular momentum follows the same type of relation. So here h cross square. So since in numerator and denominator there are square terms, so h cross square will be getting cancelled out, and we will be having g is equal to 1 plus j into j plus 1 minus l into l plus 1 plus s into s plus 1 divided by 2 j into j plus 1. So this is the relation for Landes G factor for the cell 2p 3 by 2. So for 2p 3 by 2, what we have? We have s equals to 2, sorry, s equals to 1 by 2, because 2s plus 1 equals to 2, and if we calculate then s will be 2, and for p l equals to 1 and j is 3 by 2. So if we put all these values, then we will find the Landes G factor for the 2p 3 by 2 orbital. So please put all these values and calculate and tell me the answer, what is the value for g. I will wait for a few minutes for your answer. Please calculate and tell me. So can anyone tell what is the value of g for 2p 3 by 2? So I encourage everyone to take part in these discussions, because only when you will be involved, if you discuss, then the session will be a little bit more interactive, because also the main aim of the session is to interact with you students and to clarify your doubts and to solve a few problems which will help you to solve different problems which you will be getting in your assignments. So if you don't interact in this session, so then it has no meaning basically. So I encourage you to interact a bit more. So if we put all these values, so we can calculate the value of G. Then G will be 1 plus J into J plus 1. J is 3 by 2. So 3 by 2 into 3 by 2 plus 1 is 5 by 2, minus L into L plus 1. L is half, L is 1. So L into L plus 1 is 2, plus S into S plus 1. S is half. So S into S plus 1 is 3 by 2, divided by 2 into J into J plus 1, that is 3 by 2 into 5 by 2. So 2 gets cancelled out. It is 1 plus 15 by 4 minus 2 plus 3 by 4 into, it is 15 by 2, so it will be 2 by 15. Then it will be 1 plus 5, 15 by 4 plus 3 by 4, it will be 18 by 4 minus 2 into 2 by 15, so to 1 plus 18 minus 8 by 4, so 10 by 4 into 2 by 15, so it will be 2, 3 and 2 is 2, so it is 1 plus 2 by 6, that is 8 by 6 or 4 by 3. So this is the answer. So the Landes G factor is 4 by 3 for which level? To P 3 by 2. So for 2p 3 by 2, what we got? For 2p 3 by 2, the Landes G factor value is 4 by 3. So here we can, so here we calculated. So everyone is getting the same answer. So we completed the first part of the question. The question was find the Landes Z factor for it, and then the number of substates into which the ground state will split in a weak magnetic field. So basically we want to find the number of substrate into which the ground state will split. So when we consider, let me add another slide. So we got, so we now want to calculate the number of level into which this state, that is 2p3 by 2, will be splitting. So 2p3 by 2, for 2p3 by 2 we have j equals to 3 by 2, and we want to found the splitting in a weak magnetic field. So basically here, what we mean by weak magnetic field? So the strength of a magnetic field is such that the coupling between L and S is not broken. So here J will be the, so here J has some meaning, because in a magnetic field, if the magnetic field is too high, then L and S will not couple to form J. Like if this is the magnetic field direction B vector, then we have L vector. Suppose this is L vector, and we know L is spinning around magnetic field like this. Similarly, we have S vector also. So S is also spinning around the magnetic field. So if the magnetic field is weak, then we know that due to the interaction between orbital angular momentum and spin angular momentum, then there will be total angular momentum which is known as g, sorry, which is known as j. So this is j. J also precesses around the magnetic field. So if the magnetic field strength is weak, then there will be coupling between the orbital angular momentum and spin angular momentum, and they will produce j. So here we have mm, j is 3 by 2. So if j is 3 by 2, then what is the number of levels it will be splitting? So the number of level will be the multiplicity of the level, that is 2j plus 1. So for j equal to 3 by 2, we have 2 into 3 by 2 plus 1. So it will be 3 plus 1, 4. And the mj values for this what will be the mj values for these four levels? So the mj values will be plus 3 by 2 plus half minus 3 by 2 and minus half. So for this j, it will have 4 mj values because j equal to 3 by 2, and for each j we have mj values. So for j equals to 3 by 2, we will be having 4 mj values, which are plus 3 by 2 plus half minus 3 by 2 and minus half. So basically, here it is given in weak magnetic field. So in weak magnetic field, the strength of the magnetic field is such that the coupling between orbital angular momentum and spin angular momentum to form the total angular momentum of the atom is not broken. So here here we denote it by J, N, J and Mj, because L and S have no longer meanings because it is the total angular momentum we are considering. So in a weak magnetic field, the total orbital angular momentum has meaning, and L and S are lesser, as are of less importance. So in a weak magnetic field, the energy level, which is 2p3 by 2, having J value 3 by 2, will get splitted into 4 levels, each having mj values plus minus, each having different mj values, which are these 4 values plus minus 3 by 2 and plus minus half. So basically, this is the total question. Everybody understood it, or I will explain it again? Then, if you have any doubt, then I can explain it again. So let's come to the second question. Here, the second question is: an electron under spectroscopic examination is placed in magnetic field of 0.2 Tesla. Calculate the G-man shift of a spectral line of wavelength 5000 Armstrong. In previous in previous session, we had discussed few problems like this. So basically, in last session, someone asked me about the Larmor precision. Basically, this is a question related to the Larmor precision. So here it is given the G-man shift of a sector line of wavelength, that is lambda equals to 5000 Armstrong, and it is placed in a magnetic field of 0.2 Tesla. So what we want to calculate? We want to calculate the G-man shift of a spectral line of wavelength 5000 Armstrong. So what we will calculate? We will calculate the shift of spectral line, that is delta lambda. So basically, when a external magnetic field is applied due to the torque experienced by the orbit due to the presence of the magnetic field, or also we can say that since we had the orbital angular momentum, we had orbital magnetic dipole moment. So this magnetic dipole moment, when a magnetic dipole is placed in a magnetic field, then it experiences some force, and the magnetic energy is given by mu l into b, where mu l is the orbital dipole moment and b is the magnetic field. So due to which it experiences a torque, and if this is the magnetic field b vector, then due to, sorry, let me erase this. So if this is the applied magnetic field direction, then the orbit of the electron revolves around the magnetic field. So if L is like that, and the angle between them is theta, and this angle, the angle between the, this is L. So the angle between the L vector and B vector depend upon the strength of the magnetic field. So basically, this L precesses around the magnetic field. So if the, like, it is a three-dimensional concept. Like, so if the orbit is like that, then the L vector will be perpendicular to surface like this. So like this, so there will be a cone, and this precision is called a Larmor precision, and the frequency of this precision is we given by EB by 4 pi m. So what we had, so we had the frequency due to which it revolves, the frequency is given by EB by 4 pi m, because before magnetic field there was no frequency, that is L was not precessing around the magnetic field, but when the magnetic field applied, the frequency of precision is given by EB by 4 pi m. So the change in frequency will be delta nu is EB by 4 pi m, and we know that if we consider the relation between frequency and wavelength, then frequency is equals to velocity by wavelength. So if we take its derivative, then delta frequency will be minus c by lambda square into delta lambda. So if we neglect the negative sign in the calculation, so what we will get? We will get delta lambda will be how much? Delta lambda will be lambda square by c into delta lambda into delta nu, that is change in frequency. And for change in frequency we have this, so the change in frequency is lambda square by c into eb by 4 pi m. So due to this interaction, the wavelength of 5000 Armstrong will be shifted, which is known as G-man shift, because the what is G-man effect? G-man effect is the splitting of the spectral lines in presence of an external magnetic field. Similarly, we have another effect known as Stark effect, which comes in presence of electric field. So basically here, since magnetic field is applied, the magnetic field strength is 0.2 Tesla. Here it is known as G-man shift, and the G-man shift will be delta lambda equals to lambda square by c into change in frequency, that is EB by 4 pi m. So now if we put all these values, then let's put all these values. Delta lambda will be E is 1.6 into 10 to the power minus 19 coulomb, B is 0.2 Tesla, and 4 pi m, 4 into 3.142 into m is mass of electron, that is 9.1 into 10 to the power minus 31 kg into lambda square by c. So lambda square is 5000 Armstrong. 5000 into Armstrong is 10 to the power minus 10 meter. So 5000 into 10 to the power minus 10 square by c. C is 3 into 10 to the power 8 meter per second, which is the velocity of light in vacuum. So if we calculate, we will get the shift in wavelength. So please calculate, please put all these values and calculate and tell me the answer. What will be the shift in the wavelength of the wavelength of the radiation when we place the atom in external magnetic field strength of 0.2 Tesla. Please calculate and tell me. So did anyone calculated? So yes, the value will be 0.02335 Armstrong. So this is correct, Chandrasekhar Nikam. So what we will get? We will get the value. The value will be 0.02335. 35 Armstrong. So basically, when we place an atom in an external magnetic field of strength 0.2 Tesla, the shift in wavelength of a wavelength of 5000 Armstrong will be 0.02335 Armstrong. So this question, like this type of questions we solved in the previous session. In this one type of another type of question was we needed to calculate what will be the B. So in that question, what the question type was, if a spectrometer has a minimum calibration of this much, like suppose it will be given the calibration is of 0.023 Armstrong, then in order to detect the shift in wavelength, what should be the magnetic field we should place the atom. So basically this is the reverse one. So you will put all these values and we will calculate the value of B. So when we place the magnetic field in an external magnetic field of this strength, then the G-man shift of the spectral line of wavelength 5000 Armstrong will be 0.02335 Armstrong. So anyone has any doubt regarding this question? So we will go to the next question. The question is, using the results of quantum mechanics, calculate the magnetic moments that are possible for a n equals to 3 level for an orbiting electron. So, using the results of quantum mechanics, calculate the magnetic moments that are possible for n equal to 3 level for an orbiting electron. So, for an orbiting electron, we will calculate the orbital magnetic moment. So, what is the relation for orbital magnetic moment? For orbital magnetic moment, we have mu L by L is E by 2m. We discussed in the first problem. So, what will be then orbital magnetic moment? Orbital magnetic moment will be mu L equals to E by 2m into L. So, this is the expression for orbital magnetic moment. Then, here we want to calculate the possible values of magnetic moment which are possible for n equals to 3 level. So, for n equals to 3 level, what are the L values? Because here we need L values, and for L values we will calculate different L values. We will be having different magnetic moments. So for n equal to 3, what are the L values? L value, can anyone tell? For n equal to 3, what are the values of L? Can anyone tell? For n equals to 3, the L values are 0 to n minus 1, that is 0, 1, 2. So for n equals to 3, the value of the orbital magnetic orbital at quantum number is 0, 1, 2. So if we put in this equation, if we put L equals to 0, then what we get? Then we will get mu L equals to E by 2m into 0, which is 0. Then if we put L equals to 1, and again here it is given that using the results of quantum mechanics. So in the previous question, what we are taking here, L equals to L into L plus 1 into H cross. So we will take this relation to calculate, because these relation are the byproduct of the quantum mechanical treatment of the atom. So for L equals to 1, we have, what will be L? L will be L into L plus 1 root into H cross. So what will be mu L then? Then mu L will be E by 2m into H cross into L into L plus 1 root. Then basically E H cross by 2m, and L is 1 into 1 plus 1 square root. So can anyone tell me what is this E H cross by 2m? It has some name. What is it? We have discussed this also in previous sessions. Eh cross by 2m. What is Eh cross by 2m? Eh cross by 2m is Bohr magneton, and Bohr magneton is the unit of atomic magnetic moments. Similarly, if we consider about nuclear magnetic moments, then nuclear magneton is the unit of, generally we express the magnetic moment in nuclear physics. We express the magnetic moment in terms of nuclear magneton. For that case, here m is mass of electron, but for nucleus, here m will be mass of proton. So we know that Eh cross by 2m is Bohr magneton, and for Bohr magneton, the value is Bohr magneton is mu b, and its value is 0.927 into 10 to the power minus 23 unit will be joule per Tesla. So this is Bohr magneton, and if we put this value, then we can calculate mu L. Then what will be mu L? Then mu L will be this value into root 2, because L into L plus 1 is 1 into 2 root, so it is root 2. So mu L will be 0.927 into root 2 is how much? 1.414 into 10 to the power minus 23 joule per Tesla. So the value will be 1.31 into 10 to the power minus 23 joule per Tesla. So it was for L equals to 1. Similarly, for L equals to 2, what we will get? We will get mu L equals to mu B into L plus 1 root. So this will be how much? It will be 2 into 2 plus 1 is 3. It will be root 6. So it will be root 6 mu B. So 0.927 into 10 to the power minus 23 into root 6 joule per Tesla. So what is the value of mu L for L equal to 2? Please calculate and tell me. Anyone? Please calculate and tell me what is the value of magnetic moment for L equals to 2. So it will be 1.31 into 10 to the power minus 23. So the value will be 1.31 into 10 to the power minus 23 joule per Tesla. So these are the so these are the possible values of magnetic moments when the atom is placed in a level for which n is 3. So first it will be 0 for L equal to 0, for L equals to 1, it will be 1.31. Sorry, here it will not be 1.31 because so this will not be 1.31. 0.927 into root 6 will be 2.27. So the value will be 1.31 to 10 to the power minus 23, 2.27 10 to the power minus 23 and 0. There are three possible magnetic moments for an electron which is in n equal to 3, because for n equal to 3 it has 3 L values, that is 0, 1 and 2, and corresponding to each L value there is a magnetic moment and these are calculated. So anyone have any doubt in this question, or we should proceed to the next one? So this question, as I was discussing in the previous question, here it was given we needed to calculate delta lambda, and the magnetic field strength was given. But here similarly in this question, the question we will be discussing, here lambda is given. This is dl, that is delta lambda. It is given 0.1 Armstrong, and we want to find the value of external magnetic field which is required to confirm the normal Zeeman effect. So this is the minimum resolution of the spectrometer which we can see. That is, if there is a shift of 0.1 Armstrong, then we can see it. So in order to have a split of 0.1 Armstrong, what should be the strength of the magnetic field we are applying? So we need to calculate that. So um, similar to this question, you can put all these values. So basically we can solve it in the same way. The what was the relation for it? It was delta lambda equals to lambda square by c into eb by 4 pi m. So we can write the same relation, that is delta lambda equals to lambda square by c into eb by 4 pi m, eb by 4 pi m. That implies, what will the value of b? B will be 4 pi m into c into delta lambda divided by lambda square into e, and the values are given in the question. The values are lambda equals to 6000 Armstrong, delta lambda is 0.1 Armstrong, m you know, m is the mass of electron, e is the charge of electron, c is the velocity of light in vacuum. So please put all these values and tell me the answer. I'm waiting for your answers. Please calculate by putting all these values and tell me what is the answer. So if we put all these values, it will be coming in terms of Tesla, because we are considering all in meter and kg. So if we put all these values, so we can calculate the value of magnetic field required to have a wavelength shift which we can detect by the spectrometer having resolution of 0.1 Armstrong. So if we put all the values, then what we will get, the value for the external magnetic field will be 0.5 Tesla, 0.6 Tesla, 0.595 Tesla. So like in the previous question, we had zero point 0.2 Tesla and the splitting was 0.025 or 0.023 Armstrong. So here we found that to get a splitting of zero point 0.1 Armstrong, we need more stronger magnetic field, that is 0.6 Tesla, around 0.6 Tesla. So we will come to the next question. The question is, using vector atom model, determine the possible values of total angular momentum of an F electron. So for F electron, what we have, for F electron using vector atom model. So vector atom model means we will consider here L and S, that is angular momentum quantum numbers. So for F electron, what will be L value? L will be 3, because if we consider L value and their name or orbitals, for L equal to 0 it is S, for L equal to 1 it is P, for L equal to 2 it is D, and for L equal to 3 it is F. So for F, L equals to 3, and here it is given electron. So for electron, what is spin? Spin is half. So considering the vector atom model, what will be the J value? Because here we want to calculate the total angular momentum. So for total angular momentum, the J value will be L plus S to L minus S. So if we calculate L plus S, then it will be L plus S to L minus S magnitude. So it is 3 plus half to 3 minus half. So 3 plus half is 7 by 2. 3 minus half is 5 by 2. So the two possible J values are 7 by 2 and 5 by 2. So if we want to calculate total angular momentum, then we will apply quantum mechanics, and according to quantum mechanics, the angular momentum value is given by J vector. The magnitude will be given by J into J plus 1 square root into H cross. So if we put for j equals to for j equals to 3 by 5, the j equals to 5 by 2, we will get one angular momentum. For j equal to 7 by 2, we will get another angular momentum. So for j equals to 5 by 2, the angular momentum j will be 5 by 2 into 5 by 2 plus 1 h cross. So it will be overall 5 into 7 by 4 root h cross. So we can say it is 30 root 35 by 2 h cross. Similarly, if we consider j equals to 7 by 2, so the angular momentum will be 7 by 2 into 7 by 2 plus 1 h cross, 7 by 2 into 9 by 2 root H cross it is 63 root by 2 H cross. So these are the two values. So for a F electron, the total angular momentum will be 30 root 35 by 2 H cross and root 63 by 2 H cross. So one will be corresponding to j equals to L plus S. So if we put L equals to 3 and S equals to half, because for a F subcell, for a F subcell, the orbital quantum number is 3 and spin is S equals to half for electron, because electrons have spin half particles. So if we add these in terms of vector addition, so the values will be ranging from L equals to j equals to L plus S to j equals to L minus S. So for L plus S, it will be 3 plus half is equals to 7 by 2, and for L minus S, it is 3 minus half equal to 5 by 2. So corresponding to each j values, we have magnetic moments. According to quantum mechanics, the magnetic moment have given for a j value, the magnetic moment is given by j into j plus 1 root into h cross. So for j equals to 7 by 2, the value of magnetic moment is root 63 by 2 h cross, and for j equals to 5 by 2, the magnetic moment value is root 35 by 2 h cross. So basically, these are the two possible values of a total angular momentum of an electron which is present in a F subset. Everybody understood? You can ask any doubt if you have. Okay, we will then move to the next question. The question is, find the precessional frequency of an electron. Find the precessional frequency of an electron orbit when placed in a magnetic field of strength 6 Weber per meter square. So just before few minutes we are discussing about this Larmor precession, and the frequency of precession is given by Fl equals to E B by 4 pi m, which is the frequency of the precession of the orbital magnetic moment around the magnetic field due to the torque expressed by the orbital magnetic moment due to the presence of the magnetic field. So this is the precessional frequency, which is Eb by 4 pi m, and the value of B is given. The value of B is 6 Weber per meter square with Tesla. So mass of electron is 9.1 into 10 to the power minus 31 kg. Charge of electron is 1.6 into 10 to the power minus 19 coulomb, and pi, if we put all these values, then we can calculate Fl will be, the value of Fl will be in hertz. So please put these values and calculate. Please put these values and calculate the value of Larmor frequency, which is known as precessional frequency. So please calculate and tell me what is the value. ହ୍ୟାଲୋ। ହଁ କହ। ହଁ ମୁଁ ଦେଖୁଛି, ମୁଁ କ୍ଲାସ୍ କରୁଛି ତ। ହଉ। So if we calculate all these values, if we put and calculate the value of external magnetic in the positional frequency in external magnetic field, then we get the value is 8.4 into 10 to the power 10 hertz. So if we apply external magnetic field, then the positional frequency will be 8.4 into 10 to the power 10 hertz. So let's go to the next question. The question is, which combinations of L, that is orbital angular momentum, and S, spin angular momentum, of the electrons of carbon atom should be forbidden according to Pauli's principle? So, can anyone tell me what is Pauli's principle? So, according to Pauli's principle, no two electrons in an atom can have all the four quantum numbers equal. So, what are these quantum numbers? The four quantum numbers are, what are the four quantum numbers? N, L, Ml, and Ms. So, according to Pauli's exclusion principle, no two electrons in an atom can have all the four quantum numbers same. So, for here we want to calculate the combinations of L and S for electrons of carbon atom. So we discussed a few minutes before, we are discussing about Apel's principle, which gives the distribution of electrons in a atom, that is multi-electron atom. So it is 1s, 2s, 2p, 3s, 3p, like that. For carbon, what is the number of electron? For carbon, the atomic number is 6. So here, two electron will be in S, two electron will be in this S, and two electron will be in this P. So the value, what will be the value for the last electron? So the last electron is going to 2p. So for P, L equals to 1 and S equals to half for electrons. So let's draw the P cell. So it is here, since we are considering it, the question is based on the LS coupling. So what happens in LS coupling? In LS coupling, the electrons here, in p subshell there are two electrons present. So there are two electrons. So for this electron, L equals to 1, and for this electron, L equals to 1, because here we are considering about the Pauli's exclusion principle, which tells no two electrons in a atom can have all the quantum numbers same. So here n is same for both electrons because it is 2. So n is same here. L is also 2 because both the electrons are in p subshell. So L is 2. So here n and L are equal. So here now we consider other two quantum numbers, that is Ml and Ms. So when it is, when the two electrons are present in L, then what will be the resultant L? This will be L1 plus L2 up to L1 minus L2. So if for both the electrons we consider Ml equals to, Ml is equal, that is here it is 1, 0 minus 1, but here for both the electrons L is 1. So if we consider for same L, it will be 1 plus 1, and it will be 1 minus 1. So it will be 2 or 0. So the maximum value of L for the combination will be 2, and for the minimum value of the combination will be 0. So here if L equals to 2, then for both the electrons L equals to 1 and L equals to 1. So here some similarly if we consider for spin for electron S is equals to half. So if two electrons are present, both for both electrons spin is half, so S1 is equal to half and S2 equals to half. Then in that case the total S will be S1 plus S2 to S1 minus S2. So S1 plus S2 will be half plus half 1, and S1 minus S2 will be 0. So when we do LS coupling, we take value of L, value of S, and combine them or add them algebraically to add them vectorially to form J value, and this is known as LS coupling. And this type of coupling is mainly found in case of lighter atoms like the atoms which have lower atomic number. For example, in this case, we have given carbon. So what we found? We found L equals to 1 or 0, S equals to 1 or 0. So it is 2. So here, because for Pauli's exclusion principle, no two electrons can have all the four quantum numbers equal, and also we have N and L both are equal. So here, these are here for this if we considering 2, then this L is equal, so we need to consider S unequal. So if we consider S unequal, then in that case 1 is forbidden because 1 corresponds to both half and half, but this 0 corresponds to half and minus half, so the 0 will be allowed. So if we take L equals to 2, then only then we can take S equal to 0. So the allowed combination is L equal to 2, S equals to 0, and if we take similarly L equals to 0, then we can take S equals to 1. So this S equals to 1 and L equal to 2, L equal to 2, S equals to 1, and L equals to 0, S equals to 0. These are the four combinations. So these two are not allowed. That is because for both the cases the quantum numbers will be equal, because in that case, for this case for L equals to 2, S equals to 1. This has 1 plus 1, so both have L equals to 1. And if we take S equals to 1, then it is a result of the addition of half plus half. So here S S for electron, S is half half and L is 1 1, and already we are considering for P, L is 1 1, and since both the electrons are present in P, then L is 1 and N is 2 for both the cases. So in this case, since all the four quantum numbers of two electrons are equal, then doesn't obey the Pauli's exclusion principle. So that's why the combination of that's why the combination of L equals to 2 and S equal to 1 can be taken. Similarly, we can consider for S equal to 0 and L equal to 0, because for S equal to 0 and L equal to 0, we can also verify whether it will be possible, because for S equal to 0, it is half minus half, and here for it is 1 and minus 1. So as you can see, for here in this case also, all the four quantum numbers of the electrons are equal, so it will also be forbidden. So according to Pauli's exclusion principle, since no two electrons can have all the four quantum numbers equal, then in that case we can exclude the combination of L equal to 2 and S equal to 1, as they don't obey Pauli's exclusion principle. So the two electrons must have a different value of S, that is ms, because for S equals to half we have S equals to half, we have ms equals to plus minus half, and the four quantum numbers here we are considering these four quantum numbers. So these ml we are taking here, these are nothing but the ml values, because here 1 and 1 are ml, because for l equal to 1 the electrons are present in the cell of ml equal to 1. So since ml for both cases are equal, we can't consider s for both cases to be equal. So the this particular case, that is l equal to and s equal to 1, will not consider while we are taking analysis. We are doing analysis for ls coupling or jj coupling. So everybody is clear about this problem? Okay, then we shall go to the next question. The question says the term symbol for ground state of sodium is 3 2s half. What is the possible values of quantum numbers of n, l, j and mj of the outer electron for this state? So it is very straightforward question and it is very simple. So the helium ground state is, the sodium ground state is given 3 2s half. So from these three, it is clear, because if we compare it to the spectroscopic notation, n 2s plus 1 lj, then if we compare, then we can easily say that here what will be n? N will be 3, 2s plus 1 equals to 2. So which gives s equals to half, and L is how much? For s, L equals to 0, and J is, you can clearly see here, it is half, it is J, so J is half, and corresponds to J half. What will be Mj? Mj will be plus minus half. So if we consider 3 2s half, then it has n equals to 3, s equals to half, L equals to 0, J equals to half, and Mj equals to plus minus half. So these are the possible quantum numbers. And also here we can see that s equals to 1, s equals to half, and for s equal to half we have only single electron, that is one electron, because if there are two electrons present, then it will be half plus half or half minus half. So if we, so this s corresponds to a single electron. So we can, from this spectroscopy notation, again we can say that the sodium has a single electron in its outermost shell, and we can also verify that, because for sodium, what is Z for sodium? Can anyone tell me? For sodium, Z equals to 11. Is it right? So this is the combination of electrons. This is the electronic configuration of sodium. And so if we arrange the 11 electrons for sodium, it will be 1s2, 2s2, 2p6 and 3s1. So the outermost so the last electron goes to 3s level. So and for 3s level, if we consider the 3s level, for 3s level, L is 0, S is, say, single electron, S is half, so it is 0 plus half, so J is equals to half also, and it is 3. 3, this 3 is this 3. So so we can clearly see that for sodium there is only a single electron which goes into the S cell, and the ground state is 2s half. Then we will go to the next question. The question says, find the possible values of total angular momentum quantum number. Find the possible values of total angular momentum quantum number J under LS coupling of two atomic electrons whose orbital quantum numbers are L1 is equals to 1 and L2 equals to 2. So we want to find J. What should be the J value under LS coupling? So what is LS coupling? So you can say that it is LS coupling, capital L and small a, capital L and capital S. But here it is given small l and small s. So in LS coupling, what happens? Each individual orbital contour numbers L1 and L2, they combine to form a total orbital angular momentum contour number capital Z. So capital Z is equal to L1 plus L2 plus up to, and which is their vectorial addition. So here what is given? L1 equals to 1 and L2 equals to 2. So if we add, it will be L1 plus L2 ra mod to L1 plus L2 minus 1, like that up to L1 minus L2 the mod. So for L1 equals to 1 and L2 equals to 2, we have 1 plus 2 equals to 3 and 1 minus 2 equal to minus 1. So it will be mod will be 1. So it is 3, 2 and 1. So the possible L values for these two electrons having L1 equal to 1 and L2 equal to 2 is 1, 2, 3 or 3 to 1. So these are L values. Similarly, if we consider S like L, the since it is electron, so S1 will be half and S2 will be half. Here we are not considering about the Pauli exclusion principle, that is why we can't take any particular combination, because here as we can see in question it is given L1 equal to 1 and L2 equal to 2. So both the values are different. So if the quantum numbers is different, so we can so this any combination we will be taking in the in upcoming solution, any combination we will be taking of L and S, they will satisfy Pauli's exclusion principle, as the orbital quantum number L is different for the electrons. So if we take S1 equal to half and S2 equal to 2, then what will be S? It will be S1 plus S2 up to S1 plus S2 minus 1 S1 minus S2. So for half plus half it will be 1 and plus half minus half it will be 0. So L will be 3 to 1 and S will be 1 or 0. Then we have L here. L is 3 to 1, 3 to 1, and S is 1 and 0. So for L equal to 3, S will be 1, L equal to 2, S will be 1, L equal to 1, S will be 1, and for S 0, again we will have. So for L equal to 1, 2, 3 and S equal to 1, 0, we have 6 combinations of L and S. So the combinations are, what are the combinations? The combinations are 3, so it is J. So similarly, like this addition, S1 plus S2. So similarly, what will be J? J will be L plus S to L minus S. So here in this case, 3 plus 1 is 4 and 3, 3 minus 1 is 2. So in between 2 and 4 there is another number which is 3. So these, the combination of L is equal to 3 and S equal to 1 will give rise to the J value of 2, 3 and 4. Similarly, for L equal to 2 and S equal to 1, we will get J equals to 3, 2, 1 or 1, 2, 3, because 2 plus 1 equals to 3 and 2 minus 1 equal to 1. It is 1 and 1. So 1 and 1 will be 1 minus 1 0, then 1 2, because 1 minus 1 is 0 and 1 plus 1 equals to 2. So here it is 0, so it will be 3, it will be 2, it will be 1. So these are the possible combinations of J. So can anyone tell me for this what will be the spectroscopy notation? Can anyone tell me for these values, that is L equals to 3, S equals to 0 and J equals to 3, what should be the spectroscopic term we will be notifying to, we will be using to notify this level? Anyone? 2s plus 1 Lj, since S equal to 0, so 2s plus 1 will be 1 and L is 3, so SPDF, 1F and J is 3. So similarly, if we consider for 2, 0 and 2, it will be 1D2, it will be 1P1. So here 1 is multiplicity. So as you can see that only one value of j is given here. But here if we consider, if we write for this combination the spectroscopic term, then it will be 2s plus 1, 2s plus 1 for s equal to 1, 2s plus 1 will be 3. So 3 for L equal to 1, it will be P, 3P, and for j it is 0, 1, 2. So as you can see, here 3 gives the degeneracy or multiplicity, and since the 2s plus 1 is 3 and that is the multiplicity is 3, we are getting 3 values of j, that is 0, 1 and 2. So these are the possible combinations which we will be getting if we calculate the LS coupling for two electrons which have quantum numbers L1 equals to 1 and L2 equals to 2. Then anyone have any doubt regarding this question? Because this type of question you will be getting, this type of many questions you will be getting in your any competitive exams if you are giving. Then this type of LS coupling questions are very common and they will be asked many times. So if you are clear about these things, then we can uh, solve any type of question regarding the method. Anyone have any doubt? So we will take one more question. We have 10 minutes left. So this question, the question is, the mercury atom belongs to two electron system, and from spectroscopic study it is known that the green line arises from the transition of 3p2 to 3s1. The value of spin s for this case is 1. Find the number of components into which 3p2 will split in presence of magnetic field from its no field position. So the question is a bit longer. What is the question? The question gives, we know that for mercury atom, the it belongs to two electron system. So for two electron system, the transition is 3p2 to 3s1. Here the value of spin is 1. So there are two electrons. So if we consider S equals to half for both the case, then resultant S will be either 1 or 0. So as you can see, for S equals to 1, 2S plus 1 is 3. So these 3 corresponds to these 3p2 and 3s1. These 3 correspond to 2s plus 1. So for both the cases, the value of spin is 1. So, sorry. So for both the cases, here it is also given S is 1. Then find the number of components into which 3p2 will split in presence of magnetic field from its no field position. So when there was no field, then there was no splitting. But when in presence of magnetic field, what I what I what we are discussing in previous question, so in presence of magnetic field, there is coupling between the orbital magnetic moment and spin magnetic moment, and they give rise to a formation of a new magnetic moment, which is total angular momentum, and corresponding to that total angular momentum, their total orbital magnetic moment. So for 3p2 we want to calculate what will be the number of split label it will be splitting. So for 3p2, can anyone tell me for 3p2 what is the value of j, what is the value of s, what is the value of l, and what is the value of j? Can anyone tell me for 3p2 label what is the value of s, l, and j? Anyone? So for 3p2 level, the value of s is 1, value of l is 1, and value of j is 2. So you can say here j equals to l plus s. That is, this j corresponds to l plus s. Since it is 3p2, so like if we consider l equal to 1 and s equal to 1, so we have combinations 3p, 0, 1, 2, because in previous question we are considering, like here, for s equal to 1 and l equal to 1, the combination is 3p012. So here also 3p012 term will be arising, but here we are considering only the transition which gives rise to green line, that is the transition from 3p2 to 3s1. So what are the transition? The transition is from 3p2 level to 3s1 level. So from 3p2 level, the value of s equal to 1, l equal to 1, and j equal to 2. So here this 3p2 level will split it in terms of j value, because in presence of magnetic field, the coupling between l and s, l and s coupled to form j, and corresponding to a j value we have mj values. How many mj values? We have 2j plus 1 mj values. So here in the question we have j equals to 2. So for j equals to 2, what will be mj? Mj will be 5 mj values. What are they? They are plus 2, 1, 0, minus 1, minus 2. So for j equals to mj will be 2, 1, 0, minus 1, and minus 2. So when there was no field, this 3p2 line, it will get splitted into how many lines? 5 lines, which will be corresponding to mj values 2, 1, 0, minus 1, and minus 2. So if we consider the 3p2 line, if you consider the 3p2 state, then when we will place it in a magnetic field, then due to the ls coupling, the label will be splitted into 5 labels, as it has j value is equal to 2, and for each j value we have different mj value. That is, for a particular value of j, the number of mj values possible are 2j plus 1. So if we put j equals to 2, we get 2j plus 1 equals to 5. So the number of labels in which the p orbital will be splitted in presence of magnetic field is 5. So again also, similarly, if we solve what for 3s1, what will be the splitting? For 3s1, there will be 3 splitting, because like it is 3p2, it had splitted into 5 labels. Similarly, for 3s1, it will be splitting into 3 labels. Sorry, the labels are really, so it will be splitting into 3 labels, corresponds to 1, 0, minus 1, like here 2, 1, 0, minus 1, minus 2, and the transition will be occurring corresponding to the selection rule of delta j equals to 0 plus minus 1, where j equals to 0 to j equals to 0 is not allowed. That is, from this 0 to this 0, the transition is not allowed, and any other transitions are allowed, for which the change in j values, that is the change in mj value, will be 0 or plus minus 1. So these are the transition that will be allowed. So anyone have any doubt regarding this question? So basically these are the questions I wanted to discuss with you. Anyone, does anyone have any doubt? He or she can ask me. I will try to clarify their doubts. So if no one have any doubts, then we can stop here. We will discuss few more questions, and we'll discuss about few more doubts or concepts which we will be reading in the upcoming weeks. Thank you all. Thank you all for attending the today's interaction session. Good night.